Hello, everyone. We are going to start our lecture 6, which is chapter section 1.6, more on linear systems. In this section, we are mostly going to cover interesting and useful theorems. Are not going to be too many examples or anything, so that lecture is not going to be that super long. So, we are going to start with theorem which tells us that if linear system AX equals B has two solutions, then it has infinitely many solutions. What does it mean in real life? In real life, it means that the system cannot have just two solutions, three solutions, four solutions, five solutions, and so on. If it has two solutions, it's going to have infinitely many solutions. So basically, that's going to be like anything two or more is going to be just infinitely many. How we are going to prove it? The proof. Imagine that we have x1 and x2, and they are both solutions, which means that they turn this equation into a true statement. True. That's just like a fact that they are solutions. Our solutions means that equation is becoming a true statement. What can we do next? I'm going to create solution number 3. I'm going to create it next way. I'm going to take solution number 1 and add an arbitrary constant k multiplied by a difference of solutions x2 minus x1. This solution is going to work. Well, let's talk just a second about this difference x2 minus x1, and then just go back to the solution. I'm going to label, by the way, this as solution x0. Let's check what is the difference of solutions, what kind of solution it's making. Is it making any solution? I'm going to plug in x0 or multiply it by the matrix AX0, which is going to be A, and instead of x0, I'm going to plug in x2 minus x1. I want to check solution of what is going to be this x0. Well, if I open parentheses, I'm going to have ax2 minus ax1, which is going to be eventually b minus b, which is going to give me 0. So, solution x0 solves this equation, ax0 equals 0. So it solves homogeneous equation. So x0 solves homogeneous equation. So it's not just kind of solution of my system, it solves homogeneous equation. Now, what we have in this solution x3, which I'm proposing, create, we have solution x1, which is actually a solution, right? And solution of homogeneous equation, this one, multiplied by arbitrary constant k, k, a real number, arbitrary. Let's multiply this solution x3 now by matrix A and see solution of what it's going to be. Well, I'm just going to, just plug in solution x3 as it is x1 plus k, x2 minus x1, and of course open parentheses distributing matrix A. I'm sorry, my handwriting is not looking very nice. This is because I'm writing down across standing monitor. So I know that AX1 from over here is equal to B. I know that I can take a constant outside of like product of the matrix because K is a scalar. So I can write down K, A, x2 minus x1, which I know it's x0, and I know that ax0 actually equals to 0 from this part. ax0 equals to this 0. So I'm going to have b from here plus 0 from this side, which is going to give me what? Which is going to give me b. So if I unify the beginning and the end, I'm going to see that my equation, my solution x3 actually solves my linear system ax equals b. And x3 is a solution of ax equals b. What is interesting about this solution? This solution is not just one solution. If we go back to that solution, we're going to see that we have k as arbitrary constant, which means that, well, we can substitute any number for k, and that's still going to be solution. Because there are infinitely many k's, and we are going to have infinitely many solutions. Well, we proved our theorem that if system has two solutions, it's going to have infinitely many solutions. Now, guys, what I'm going to do, I'm going to copy one more time my special solution x3. And I'm going to label it just x. And this one x1 plus k. And I'm going to label this difference as x0. Guys, what we see in this solution, which describes actually infinitely many solutions, we see that it consists out of solution of ax equals b. And we are going to call this particular solution. Why do we call it particular solution? Well, we know that there are going to be infinitely many solutions. So just one of them is going to be particular solution. Also, what is this? X0 is solution of homogeneous equation. Solution of homogeneous equation. So what we do have in the sum that any solution, which can be x3, right, can be represented as a sum of particular solution plus arbitrary constant multiplied by solution of homogeneous equation. This is a very fundamental conclusion, which is going to be used a lot in other different systems where we have like two possibilities, have non-homogeneous system and homogeneous. So this is going to be called general solution of non-homogeneous system. General solution of non-homogeneous system. We see that general solution of non-homogeneous system is going to consist out of particular solution, can be x1 or x2, and the solution of homogeneous system multiplied by any arbitrary constant. And all other possible solutions are going to come into it. I did not prove this, but eventually we are going to prove it. Okay, so that was a theorem. Now I'm going to make a conclusion from this theorem. So guys, as a conclusion, what we are going to have, we know that system AX equals B can have 0 solutions, right? It can have 1 solution. And according to the just proved theorems, it can have infinitely many solutions. So there are just 3 options. No solutions when the system is inconsistent. 1 solution. Well, we remember that 2 by 2 system, for example, describes 2 straight lines. They intersect in 1 point. That's 1 solution. And 2 lines intersect in infinitely many points, infinitely many solutions. We don't have any like other options like 3 solutions or 15 solutions. Okay, so that was my first theorem. Now, guys, I'm going to prove my second theorem. Actually, today we're planning to prove like maybe 3 or 4 theorem. I'm going to label it as theorem 2, okay? But I did not label the previous one as theorem 1, theorem 2. If A, matrix A, sorry, my A doesn't look very nice. If matrix A n by n square matrix A is invertible, then equation AX equals B has only one solution, and that solution is going to look like X equals A inverse multiplied by B. Well, so what is given? That matrix is invertible. I'll need to prove that it has only one solution. Well, I'm not going to try to build contradiction here. I'm just going to write down system AX equals B. And imagine that X here is any arbitrary solution. Now, I'm going to multiply this equation by A inverse on the right. So I'm going to apply A inverse. How do I know that there is an A inverse? Because A is invertible. Now I know that A by A inverse is identity, and the right side is going to stay as it is. Well, the right side is what? Product of two matrices, matrix A inverse and B. We know that there is only one matrix with results from the product. There is not going to be like options to have like two different matrices from the same product. So where X is an arbitrary solution, it's going to be equal the unique matrix A inverse B. Because we can build this one only one way. Only one. Then this is going to be also only one because there is no other ways to do it. And if you have two different solutions, eventually they are going to have same expression, which is going to mean that they are same solutions. So this proof is kind of silly, probably, to label that I proved. And we used already in the previous section the way of finding X by using inverse. So if matrix has inverse, there is only one solution. Okay. Next theorem. Theorem number 3. Okay, theorem number 3 is going to be long theorem because it's going to consist out of 2 parts, but that's an interesting theorem and we're going to prove both parts. Okay, theorem. If A n by n is square matrix, then from the statement 1 that well, let me first introduce matrix B2. If A n by n and B a same size square matrix, if we have two square matrices A and B, then conclusion number 1 from B multiplied by A equals identity follows that B is equal A inverse. Number 2 from A multiplied by B equals identity follows that B is A inverse. Not very clear, right? Why do we need to prove this theorem about inverse? I'm going to kind of put over here definition of inverse so you can see what we are trying to prove. What is definition of inverse? B is A inverse if BA equals AB and equals identity, right? So we call matrix B inverse of matrix A if we multiply that matrix B on the left and on the right side of A, and we still get identity. What we are trying to prove? That we only have half of the statement, this one, it's already going to be inverse. Or if we only have this half of the statement, the second one, it's already going to be inverse. So basically, guys, when we prove this theorem, we don't need to prove both of this. BA equals AB equals inverse. We just can prove either like left one or the right one. So the theorem is telling us that if you multiply some matrix by 8, its identity, then that matrix is inverse. And you don't need to check if you need to multiply it on the opposite side. So left or right, doesn't matter. I'm going to prove both of them because proofs are slightly different in both cases. So I'm going to prove number one. Number one. So what I'm going to do, guys, I'm going to write down equation AX equals 0. Homogeneous equation with matrix X. Well, can I do this? Yes. Can use any matrix and put X's, multiply, and set it up to 0. Does it have a solution? It doesn't have a solution. I don't know yet, but you always can create this equation as you like can create equation AX equals B, like for normal numbers. Now, guys, what I'm going to do with this equation, that's homogeneous equation, right? I'm going to multiply this equation on both left and right side by B. So I'm going to do it B, A, X, and here B, 0. Now, what is BA? According to my statement number one, part of the assumption, BA is identity. What is B0? If I multiply any matrix by 0 vector, I'm going to get 0 vector again, right? What is identity by X is just X. And what I have actually, that X has like this system, homogeneous system, has only trivial solution. From the theorem of section 5, remember last theorem in section 5 was like 4 parts theorem. From that theorem, because it has only trivial solution, it's going to mean that A as inverse. I'm going to write down theorem from 1.5 with A, B, C, D cases, which we proved like a circle has inverse. I'm going to even write down A inverse. Now, I'm going to write down the statement B, A equals identity and multiply this statement by that A inverse. The theorem tells if homogeneous system with that matrix has only trivial solution, then matrix has inverse. I'm going to use that inverse and multiply by it on the right. Well, what I'm going to have, because A and A are inverses, I'm going to get identity here, right? And here I by A inverse is A inverse. And B by identity is just B. And I get that because A has inverse, this inverse equals B. And I actually proved my theorem. Sorry, everything jumped somewhere away. Well, that's my proof. So I'm going to put this dark square that my B is actually inverse. So I proved it. Now, guys, I'm going to prove B second part. Second part is a little bit like different. So let me put separation so we cannot not mix them. So part two. What is given in part two? In part two, given that AB equals identity. So that's given, given. And we'll need to prove that B equals A inverse, need to prove. Okay, what I'm going to do, guys, here I'm going to start with a system Bx equals 0. And I'm going to do the same trick with it. I'm going to multiply it by A. A, Bx equals A 0. Why I'm doing this? Because I have to have A on the right side of B. From given, AB equals identity, just AB equals identity from given X. And here 0 equals 0 and X equals 0 again. So actually this homogeneous system, slightly different from previous case, has only trivial solution, means that B has B inverse by the same theorem from section 5, right? What I'm going to do, well, I'm going to from here, I'm not gonna actually multiply this statement by b inverse, though I can do that. Let's do it. Let's finish it this way and then kind of give a little bit more explanation. So I'm going to use a given part that a multiplied by b equals identity, and I'm going to multiply it by b inverse on both sides. By b inverse here and ib inverse here. Well, as usual, this is identity, this is A, this is B inverse, and I'm going to get A equals B inverse. Well, it's not exactly what we wanted to prove, right? We actually wanted to prove that B is A inverse, but we proved that A is B inverse. Well, if you remember the definition of inverse, tells us that B is A inverse if BA equals AB. But for matrix A to be inverse of B, that's going to be the same statement, right? If you consider matrix B as a regional matrix, then A is going to be inverse of it because you multiply A by left and right side and kind of get the same identity. So actually, when we write down this statement, B is inverse of A and A is inverse of B. So what does it mean, guys? It means that if A is like inverse of B, then according to that statement, B is inverse of A. And if B is inverse of A means that B equals A inverse. Well, again, because the definition which we have over here is symmetrical for A and B, you can say that this is definition that B is inverse of A, but also you can say that A is inverse of B. And what we have over here is A is inverse of B. B inverse equals A. Means that B is going to be equal A inverse. Yes, I proved it. So now we don't need to prove both parts of definition. We just can use one part of definition. Very nice, right? I mean, kind of long proof, but kind of nice one, right? Okay. And guys, I have the last theorem about inverses, and that's going to be theorem number 4. Need to scroll this up. Oh, my squares are becoming smaller, smaller, and smaller. Theorem 4. Theorem 4 is going to tell us if product of two matrices has inverse, then B and A have also inverses. And guys, I'm talking here about square matrices. So I did not write it down anywhere because it's going to take me some time to write it down, but I'm talking about square matrices. So, well, what this statement means. Some time ago, we had a theorem that, let me kind of give it for comparison. I don't know where to put it, but I'm going to put it over here for comparison. Compare. We had a theorem which was looking like this. If A has A inverse and B has B inverse, then AB product has inverse and it equals B inverse by A inverse, right? Here, guys, we are trying to say the opposite. Now, if the product has inverse, then each matrix is going to have inverse. So before we proved that if both A and B have inverses, then the product is going to have inverse. Now we're saying if product has inverse, then each A and B is going to have inverse. Trying to prove actually converse of it, right? Uh, or let's say we are trying to show that these two statements, the product has inverse and each A and B has inverses, are equivalent because we kind of proved it one direction. Now we are going to prove it opposite direction. Okay, let's see how to prove it. It's not going to be too difficult, actually, in this case. So, what is given? Imagine that product inverse is given. Like that's given, right? We're going to label it as matrix C. Matrix C, that's inverse. What I'm going to do, guys, I'm going to write down that A, B by that matrix C is supposed to be identity. Why? Well, because C is inverse of the product, right? Now, what I'm going to do, I'm going to remove this parenthesis. I'm going to write on A, B, C. And I'm going to consider this matrix as a second matrix multiplied by A and give me inverse. And I'm going to go to this theorem. I multiply by A some matrix and get identity. Let me find it over here. A multiplied by some matrix is equal identity, then that some matrix is inverse of A. So I'm going to write down that inverse of A from that theorem, from theorem number 3, is equal B multiplied by C. Now I'm going to go back. What was C? C was actually A, B inverse, which was given that exists. So that's going to be inverse. So I proved that A has inverse. The second proof for B. Now I'm going to prove that B has inverse. What I'm going to do is, well, I'm going to start kind of same way. I'm going to label C equals A, B inverse. Sorry, far no place. Now, instead of multiplying it, uh, like C from the right, I'm going to multiply C from the left by AB. Well, this statement's supposed to be true. You have inverse, which is C, right? And you multiply it by direct product. Now I'm going to rearrange parentheses. And again, by theorem 3, I'm going to state that this one is B inverse. I'm going to write on B inverse equals CA, or it equals AB inverse multiplied by A. So kind of we proved the theorem. So there is B inverse, and actually we give the formula. There is a B inverse. What I'm doing wrong? I'm coloring these squares. Actually, we start a square with empty. We start the proof with empty square, and we kind of finish it like with color. So we proved that there is A inverse and B inverse, and they are looking actually like product inverse of the product multiplied by either A or B on the left or on the right. And I think that's going to be it from this section 1.6. So thank you for your attention. I think it was a very short lecture for us. Okay.